Hello, my friends, and welcome. Today we are going on a fantastic journey deep into the quantum world. We are going to solve a mystery, you see, a real puzzle that has stumped physicists for a very long time. It's a story about a disappearing act, a very, very clever trick with time, and in the end, a showdown with the world's most powerful supercomputer. So, come, let's begin. Just imagine for a moment you shout into a beautiful canyon, but instead of hearing your voice echo back, the sound just vanishes. Instantly, it dissolves into the wind. This is exactly the problem we face in the quantum world. When you have many quantum bits, or qubits as we call them, all interacting, any information you put in gets scrambled. It just spreads out everywhere, gets all tangled up, and for all practical purposes, it's gone. So the question is, how can you learn anything if your experiment erases itself before you can even properly measure it? A real head-scratcher, isn't it? And this isn't just a thought experiment, it's a real phenomenon. You see, the usual way we measure things, using what we call time-ordered correlators, is like giving the system a little poke and then seeing what happens a moment later. But in these very complex systems, the signal from that poke just fades away, exponentially fast. Poof! In a fraction of a second, it's completely lost in the noise. It makes seeing the subtle rules that govern the quantum world almost impossible. But now, here comes the truly brilliant part. What if you could somehow turn back the clock? Not literally, of course, we are not building a time machine, but what if you could create a kind of quantum echo that reverses all that scrambling? This is the beautiful solution that the scientists at Google Quantum AI came up with, a method to, in effect, rewind the quantum evolution and get back the information that seemed lost forever. The special tool for this magic trick has a bit of a complicated name, an Out-of-Time-Order Correlator, or OTOC for short. Now, please don't worry about the name. Just think of it like this. You send a message forward in time, you let it get completely mixed up and scrambled, and then you send a special unscrambling signal, and then you run time backwards. The OTOC basically measures how well your original message comes back together. It's a way of listening for a very faint echo, even in the middle of a storm. So the OTOC works a bit like an interferometer, but it's an interferometer for time itself. What it does is send quantum information down two different paths. The first path is simple. It goes forward in time, and then it comes backward. The second path is almost the same, but with one small difference. We give the system a little poke, a little nudge, right in the middle of its forward journey. By comparing how these two paths interfere with each other at the end, scientists can figure out exactly how that little poke spread and scrambled the information. So clever. Okay, so the theory is very elegant, very beautiful, no? But the real question is, does it actually work in practice? This is where we must put on our detective hats. We're going to follow the clues from the Google Quantum AI team as they used this technique on their own quantum processor, hunting for a very, very subtle effect, a sort of ghost hidden deep inside the machine's programming. And look at this. Here is our first clue from the experiment. You see that single red qubit at the beginning? That is our piece of information. Now, just watch. As time moves forward from 6 cycles to 12 to 18, look how the information spreads outwards. It looks like ripples in a pond, no? This beautiful pattern is what we call a light cone. This is the information scrambling, happening right before our very eyes, exactly as the theory predicted. And here is the crucial point. Look at this chart. If we use the normal, old measurement method, the signal it falls off a cliff. It's gone. But with our clever OTOC method, with this time reversal echo, look, this signal is strong, it's clear, it's there. We can finally see into this scrambled quantum world. The echo has come back to us. So what did this powerful new lens reveal? Well, it found the ghost we were looking for, a deeply hidden effect called large loop interference. This is a special kind of quantum correlation that is completely, totally invisible if you use the simpler measurement techniques. It's like a secret handshake that only the most complex quantum systems share. You see, in quantum mechanics, information takes all possible paths at once. It's a very strange idea, I know. Now, the diagram here shows that a simple OTOC can see the patterns from simple, small loops. These are like the main roads. But to see the patterns from these big, complex, large loops, where 4 different quantum paths all interact, my goodness, that is the real challenge. And this faint, complicated signal is exactly what the researchers were trying to catch. So they found the ghost. They measured this large loop interference. But you might be asking,
Professor, why is it such a big deal? Because this is where our detective story becomes a heavyweight championship fight. In one corner, we have the 65-qubit quantum processor, and in the other corner, we have the most powerful supercomputer on the entire planet Earth.
And here it is, the proof, the smoking gun, as they say. This graph shows the direct measurement of that incredibly complex signal performed right on the quantum processor. The data points, you see them, they show a clear, undeniable signal. They successfully measured something that is notoriously incredibly difficult to even calculate. And why is it so difficult? Because calculating this is a task of just mind-boggling complexity. The number of possible paths the information can take grows exponentially. So for a system of this size, even the world's #1 supercomputer, a machine called Frontier, it just cannot keep up. For all practical purposes, the problem is intractable.
And now, my friends, get ready for the punchline. The quantum processor, it took just over 2 hours to measure this result. 2 hours. And to calculate the same result, the estimation for the Frontier supercomputer is 3.2 years. Not hours, not days, but years. Can you believe that? This is a clear, undeniable demonstration of what we call quantum advantage.
So, the mystery is solved, and our quantum computer has won the fight. But what can we do with this new power? This is not just some academic exercise. This technique, it lets us do something truly remarkable. It allows us to learn the fundamental rules of other quantum systems. This process is called Hamiltonian learning. A Hamiltonian is basically the rulebook for a quantum system, and this process lets us learn that rulebook. It's quite simple, really. Step 1, you take a real thing you want to understand, say a complex molecule, and you measure its OTOCs. Step 2, on your quantum computer, you simulate that molecule with some settings you can change. And step 3, you adjust those settings until your simulation's OTOCs perfectly match the real ones. And when they match, bingo, you have created a perfect digital twin of that molecule. And they proved that it works. They ran a test where they created a system with a secret parameter that only they knew. Then they asked the quantum computer to try and learn that secret parameter. And look at this graph. The curve takes a sharp dip right at the correct value. That is the quantum computer finding the right answer. It successfully reverse-engineered the system. Isn't that fantastic? And the implications of this are just enormous. Imagine being able to create perfect models of new materials for solar cells or better batteries. Imagine designing new medicines by precisely simulating how they interact with our bodies. This technique of learning a system's rules opens up so many doors to discovering new physics, to creating incredible technologies. It is truly unlocking the power of the quantum world. So we have gone from a vanishing echo to a clear signal that outpaces our best supercomputers, and finally to a new tool for discovery. We have found a way to ask the quantum world its deepest questions and actually get clear answers. And this leaves us with one final, very exciting thought. Now that we can finally probe the quantum world's deepest secrets, what do you think we should ask it first? Thank you for watching.